Alice, Bob, and Eve explain GHZ States.
I've set up a little card game for you. These 3 cards are either all aces or all kings, but you have to guess which.
You know, this reminds me of a fascinating quantum phenomenon called GHZ States.
Oh, GHZ States, named after Greenberger, Horn, and Zeilinger. They're one of the most striking examples of quantum entanglement.
How do my playing cards relate to quantum entanglement?
Your cards are in one of 2 definite states, all aces or all kings. In a GHZ state, 3 or more quantum particles are entangled in a special way, where they're in a superposition of 2 maximally correlated states.
Imagine if your cards could be in a superposition of all aces and all kings simultaneously until someone looks at them.
So what happens when you measure particles in a GHZ state?
That's the fascinating part. When you measure just one particle, you collapse the entire system. If you measure one particle and find it in state ket 0, all other particles will also be in state ket 0. If you find it in state ket 1, all others will be in state ket 1.
Here's another example. I have some buttons in my pocket. Think of these 3 buttons connected by thread. In a GHZ state, they're either all black or all white, nothing in between. Measure 1, and you instantly know the color of all of them.
That doesn't sound too strange. Couldn't they have been predetermined to be all black or all white?
That's where the quantum weirdness comes in. Before measurement, they're genuinely in both states simultaneously, and GHZ states show this in a particularly dramatic way.
Local hidden variable theories, the idea that particles have predetermined properties, predict one result for certain measurements on GHZ states, while quantum mechanics predicts something completely different.
And experiments confirm quantum mechanics is right. GHZ states provide some of the strongest evidence against local realism, the idea that particles have definite properties independent of observation.
Beyond the philosophical implications, do GHZ states have practical applications?
Absolutely. They're useful in quantum communication protocols, quantum secret sharing, and as resources for quantum computing.
And they've been created in laboratories using photons, trapped ions, and superconducting circuits.
So my simple cards can only be all aces or all kings, but never both at once. Yet quantum particles can exist in that impossible-sounding state until we look at them.
And even more incredible, when they do choose a state, they all choose together, instantly, no matter how far apart they are.
It's like having 3 dice that can show all possible numbers at once. And when one die finally settles on a number, the other 2 instantly show the same number, even if they're on opposite sides of the universe.